Yes, good morning once again. Welcome back to the series of lectures on embedded systems. And today we are going to discuss about embedded hardware design. So this embedded hardware design unit will gives you a complete over idea. Overview. The complete overview about the embedded hardware concepts and their design approaches. Okay, so let's go into the topic. So the unit 2 syllabus is we're going to look into the topics about analog and digital electronic components, IO types and their examples, serial communication devices, parallel device ports, wireless devices, and timers and counting devices, uh, application of a timer device, that is Watchdog timer, and the final is real-time clock. Okay, so let's move on to the syllabus. Right, so the objectives for this unit is uh, to know about the communication devices and basics about VLSI and integrated circuit design. And the outcomes from this unit is going to be the hardware components. The students will learn about the hardware components required for an embedded systems and the design approach of an embedded hardware and the various elements of embedded hardware and their design principles. So these are the outcomes, and the topics that we are going to discuss is are the same topics from your syllabus concept. Okay, right. So first, so what is meant by analog basically? So analog in general sense means some continuity form. Okay, that means analog quantities will always be considered as a continuous forms. Okay, so likewise, what type of analog activity does going to be handled by the concerned devices are going to be considered as analog electronic components. Okay, so resistors, capacitors, diodes, inductors, operational amplifiers, transistors, etc. So these are the commonly used analog electronic components in embedded hardware design. Okay, so what is resistor? The resistor limits the current flow inside a circuit. Okay, so the main purpose of a resistor is to limit the current flow uh, inside the circuit in such a way that what amount of current that is needed by the device is going to be supplied by the resistor. Okay, and the applications of resistor is uh, interfacing of LED circuits and buzzer units. Okay, so by connecting the concerned terminal, that is the port pin section of a microcontroller through current limiting resistors, okay, we can achieve the operation of a resistor with the um, related applications. Okay, so this is considered to be a typical example for the uses of resistors in embedded application. Okay, right. So next is capacitors and inductors. So what is a capacitor and what is an inductor? Right. So capacitors and inductors are used in signal filtering and resonating circuits. Okay. Right. So what is signal filtering? I can say that in any circuit there is a requirement of an AC signal or a DC signal. Okay. So in that sense, uh, if at all if we want to make use of an AC signal, then automatically we need to filter the DC quantity. Okay, that means we need to remove the DC quantity. So likewise, the combination of a capacitor and inductors can be used as filtering and resonating purposes. Okay, and next is reset circuit implementations, matching circuits for RF designs, power supply decoupling, etc. are the examples for the usage of capacitors in embedded hardware circuit. Okay, so these are some of the circuit based applications that can be making use of the capacitor and inductor combinations. Okay, so that they can provide the necessary things required for the circuit, right? Next, so some of the different types of capacitors that are going to be used are electrolytic capacitors, ceramic capacitors, tantalum capacitors. Okay, so these are considered to be the commonly used capacitors in embedded hardware design. Okay, so inductors are widely used for filtering the power supply from ripples and noise signals. That means, so if we want to make use of a DC supply, so automatically we need to filter out the AC component what is there inside the existing power. Okay, so that is how we are going to remove the ripple section, that is the AC quantity inside your signals. Okay, so next, inductors with inductance value. That means we are going to select the inductors in a microhenry range. Okay, likewise for capacitors we are going to select a microfarad range. Okay, and with the use of microhenry inductors, we can going to make use of the inductor for filtering and matching circuit implementations. Okay, so these are the representations of capacitor and inductor circuits. That means the left part of your picture shows you the different types of capacitors, and the right section will provide you with the inductor circuitry. Next, diodes. Okay, so what is a diode? Basically, a diode is considered to be a device which is going to be operated as a switch. Okay, so PN junction diode, Schottky diode, Zener diode, etc. are the commonly used diodes in embedded hardware circuits. Okay, so when compared with the Schottky diode, PN junction diode is considered to be not that much efficient. Why? Because the voltage drop across the diode during the conduction time. So when compared with the PN junction diode, for a Schottky diode, it is very low. That is, it ranges from 0.15 volts to 0.45 volts. When compared to a normal ordinary PN junction diode, the range will vary from zero point 0.7 volts to 1.7 volts. So that is why we are going to make use of the Schottky diode for uh, operations. Okay, I mean the applications, right? And next, also the current switching time of a Schottky diode is very small. Why? Because the conductivity voltage is very low. That is why the switching time of a Schottky diode is also very small. Okay, so these are the representations. Diodes and symbols. The first one is the PN junction diode, second one is the Schottky diode, and third one is the Zener diode. Okay, right. Next, so a Zener diode acts as a normal PN junction diode. That means a PN junction diode, in terms of operation, it is only considered in a forward bias operation. Okay, so whereas the Zener diode can be operated in both forward bias and reverse bias condition. Okay, right. So it also permits the current flow in the reverse direction. So that is why it is going to be operated in reverse bias condition. So it also permits the current flow in the reverse direction if the voltage is greater than the junction breakdown voltage. So this is the condition which is to be considered for a Zener diode to be operational. Okay. It is normally used for voltage clamping application. That is, a Zener diode is normally used for voltage clamping application. That means if we want to modify the operating voltage, we can make use of a Zener diode. Okay, right. Next, it also provides some important application functionalities, that is the reverse polarity protection, voltage rectification, freewheeling of current produced in inductive circuits, clamping of voltages to a desired level. Okay, so clamping of voltage to a desired level, that means we can also consider one of the example, that is the real-time implementation, that is the brownout protection circuit implementation using Gina diode. So here brownout protection is nothing but to safeguard the operational voltages inside your circuit without making the circuit to be broken down. Okay, so these are some of the examples for the usage of diodes in embedded applications. Okay, next is transistors. So what about transistors? So transistors in embedded applications are used for either switching or amplification purpose. Okay, so either we can make use of the transistors as switching purpose, that is as switches, or otherwise we can consider the transistor for amplification purpose. So what quantity is going to be amplified means, so the voltage quantity or the current quantity, okay, or otherwise the power quantity can be amplified, right? So to mean what amount of quantity that is needed at the receiver end can be provided by the transistors. Okay, and next in switching applications, basically the transistor can be either in on state or off state. Okay, so these are the two states that a transistor can be operated, right? Next, so in amplification purpose, the transistor is considered to be always in on state, that is the on state is also, I mean is comparatively it is a partially on state. Okay, so that is why during the amplification activity only the transistor will be in a on state, and after the operation is successfully done, automatically the transistor will be moving into off state, but the off state is not the original off state. Okay, so why? Because the amplification purpose or the amplification activity must be done continuously. Okay, right. Next, so we are going to make use of the transistor to be operated in three different configurations, that is based on their terminal terminal combinations. Okay, so that is emitter, base, collector. Okay, so the common or the efficient way of operating your transistor for your applications is a common emitter configuration. Okay, so in that also we are going to make use of the NPN transistor. Okay, so the common emitter configuration of NPN transistor is widely used in switching and driving circuits in embedded applications. Okay, right. Next, so some of the examples that makes use of the transistor as their main supporting thing are the relay units, buzzers, stepper motor, driving circuits. Okay, so these are considered to be the examples for common emitter configuration based driver circuit implementation using transistor. Okay, and this is the original representation of the transistor, and these are the symbols. Okay, so that is first one is the NPN transistor configuration, that is is a common emitter configuration, and the second one is PNP transistor, okay, with common collector configuration. Next, so coming to the next part, that is the digital electronic, the other end of the analog electronic component section. Okay, so what is digital? So basically the name digital means discrete quantity. Okay, so likewise digital electronics deals with digital or discrete signals. Okay, so microprocessors, microcontrollers, and system on chips works on digital principles. Okay, right. So embedded systems employ various digital electronic circuits for glue logic implementation. So hope you are new to the word glue logic, but I think that this glue logic concept is already known to you in your VLSA subject. Okay, so what exactly glue logic means? The glue logic is the custom digital electronic circuitry required to achieve compatible interface between two different integrated circuit chips. Okay, so what it means is, I can say that if I want to implement a logical AND operation, okay, so automatically what I can do is, I can configure two different ICs where the logical AND operation can be implemented, and automatically they will be connected in a fixed manner. Okay, so there won't be any changes. Right, next. So some of the examples that are making use of the glue logic for their implementations are address decoders, latches, encoders or decoders, etc. Okay, so these are some of the examples for glue logic circuits. Okay, and next is TTL logics, CMOS logic, etc. So these are some of the standards describing the electrical characteristics of digital signals in a digital system. Okay, so in order to analyze the electrical characteristics, that means how the circuit response is, we need to make use of the TTL logics or CMOS logic based implementation to realize the conditional functionalities. Okay, right, next. So the next topic is the open collector and tri-state output. So in this topic, we are going to consider the transistor as the key element to be considered for operation purpose. Okay, so first is, let's see the open collector thing. Okay, so open collector is an IO interface standard in digital system design and a common type of output found on many integrated IC chips, which behaves like a switch that is either connected to ground or disconnected. Okay, so I hope that open collector, what is open collector? Basically, for a common emitter configuration, the emitter is to be connected for a ground terminal. Okay, and the base terminal is considered to be as a input. And what about the collector? Actually, the collector is, we are going to take the output across the collector terminal, but here we are considering the collector is uh, in a open configuration. Okay, so that is why a open collector is an IO interface standard. Okay, so it is a normal output section only, but what happens here is, it acts as a switch. Okay, but originally there must be a physical connection to realize the operation of a transistor as a switch. But what happens here is, we are not connecting the collector to any terminal. Okay, right, next point. So instead of outputting a signal of a specific voltage or current, the output signal is applied to the base of an internal NPN transistor whose collector is externalized, that is open contact on a pin of the IC. So what it means? So in order to continue the operation, we are going to return back the output section, that is from your collector terminal, to the input section, that is the base section. Okay, so automatically this may be considered as a feedback section element also. Okay, so why? Because it may give the standardized, it may give the support. Okay, so this is how the open collector configuration can be, operated. Right, next. The emitter of the transistor is connected internally to the ground pin. So here the emitter is connected to a ground. Okay, so this is the representation of open collector configuration. So here you can observe the collector pin is directly shown as in, openly. Okay, and here you can also see that the emitter terminal is grounded, and again the base section is inputted with the open collector output. Okay, right, next. For the output pin to function properly, that means at the collector end, the output pin should be pulled to the desired voltage for the output device through a pull-up resistor. So what happens here is actually the output section is not connected to any section or any pin. So we need to maintain the output at a fixed voltage level. Okay, so how this is going to be achieved is with the help of a pull-up resistor. Okay, so the output signal of the IC is fed to the base of an open collector transistor. Okay, the output of the signal, the output signal of the IC is fed to the base of an open collector transistor, as already we discussed. And when the base drive, when the base drives to the transistor, that means from the base input, if the transistor is in on state and the collector is in open state, the output pin floats. What happens here is there is no connectivity from the output section to the input section. Automatically the output is considered to be in an open state and the output pin floats. That means there is no valid contact. So this is how the output state with no valid contact or the output pin floats is also known as a high impedance state. Okay, that means at the output section there won't be any logical combinations, either logic high or logic low. Okay, so nothing will be either 1 or 0 will not be appearing at your output, so it will be considered to be a high impedance state. Okay, next. If a pull-up resistor is connected to the output pin, okay, if a pull-up resistor is connected to the output pin, when the base drive is on, the output pin becomes at logic 0. Okay, so with the help of pull-up resistor we are going to retrieve the condition at the output. Okay, so what condition that we are achieving is, if a pull-up resistor is connected for the same circuit configuration, and automatically when the base drive is on, the output pin becomes a logic 0. Okay, or otherwise it is having a 0 volts at its output pin. Okay, and the other combination, that is with a pull-up resistor, if the base driver is 0, that means if the base driver is off, the output will be at the logic high, that is the voltage that is being applied at the collector terminal is equivalent to your supply voltage, that is VCC. Okay, so these are the configuration and this is the representation for your circuit with a pull-up resistor. Okay, right, next. So the advantage of open collector output combination in embedded system design are, okay, the first one is it facilitates the interfacing of device. That means it provides an advantage of interfacing in between devices and operating at a voltage different from the IC with the IC. That means we can modify the voltages, or otherwise we can modify the circuit connections that are going to be operated with different voltages. Okay, so automatically what happens here is it eliminates the need for additional interface circuits for connecting devices at different voltage levels. The first advantage that we are going to achieve with the help of open collector output configuration circuit is we can we can combine multiple integrated circuits that are going to be operated with different voltage values. That means I can say that a 5 volt operation or a 12 volt operation or a 3 volt operation can also be achieved with the help of a open collector output configuration. Okay, right, next is an open collector configuration supports multi-drop connection. That means we can drive multiple slave combinations or multiple slave lines from a single master. Okay, so this can also be achieved efficiently with the help of open collector configuration. Right, next. So it is easy to build wired AND and wired OR configuration using open collector output lines. Why? Because with the help of a pull-up resistor we are going to achieve the output state, that is a logic 0 or a logic 1. Okay, so likewise we can implement a hardwired implementation of AND logic and OR logic. So okay, So this open collector configuration will gives you that advantage, right? Next combination, the next implementation with a transistor is the tri-state output. Okay, so let's see the thing. So in the heading itself, we can observe that a tri-state means it is having three states. Okay, so the two states are known to everyone, that is the logic 0 and logic 1 is known. Okay, and the third state, that is a high impedance state. So it is the state that we discussed in the previous topic, that is the uh, open collector output configuration topic. Okay, so the same way we are going to consider the third state. Okay, so let's see the first point. The output of a standard logic device has two states, namely logic 0 and logic 1, whereas tri-state devices have three states for the output, namely logic 0, logic 1, and the high impedance, that is the floating gate state. Okay, so a tri-state logic device contains a device activation line called device enable. So how we are going to validate the three states for the transistor operation is with the help of a device enable line or a device activation line. Okay, so let's see how the device activation line is going to be operated. Okay, so when the device enable line is activated, that means if it is selected, automatically the device acts like a normal logic device and the output will be in any one of the logic conditions. That means if at all, if the device enable is activated, that means if we assigns a value or if we set a value of logic 1. Okay, so automatically what happens is uh, an active high enable input will be at logic 1 and an active low enable input will be at logic 0 will be selected, and the device will act as like a normal logic device and the output will be in any one of the logic conditions, that is a logic 0 or logic 1. The other combination is when the device enable line is deactivated, that means if we are considering the device enable line as deactivated, automatically the logic 0 for an active high enable input, that means you are considering a 0 for 1, and the same logic 1 for an active low enable input, that means 1 for 0. So what happens is the output of the logic device enters in a high impedance state. Okay, the output of the logic device enters in a high impedance state and the device is said to be in the floating state. Okay, so that means there won't be any valid connection at the output. So this is the functional table or the truth table for a tri-state configuration. So you can see here we are having two inputs, that is A and B, and the output is C. So for the combinations of logic 0 and logic 1, we can get the outputs as a logic 0 and logic 1. But if we are considering that there is a don't care condition for any one of the input, automatically the output is considered to be a logic null state, that means a high impedance state or a floating state. Okay, so which is represented as Z with letter Z. Okay, right. Next topic is logic gates. So what are logic gates? Logic gates are considered to be the building blocks of digital circuits. Okay, so what is the presence of or what is the importance of logic gates is they control the flow of digital information by performing a logical operation of the input signals. Okay, logic gates control the flow of digital information by performing logical operation of the input signals, or otherwise they will maintain or they will manage the bit flow, that is zeros and ones, right? Next, so depending on the logical operation, okay, so what type of operation or what type of operation that a logic gate is going to be used, the logic gates used in digital design are classified into AND gate, OR gate, XOR gate, NOT gate, NAND gate, NOR gate, and XNOR gate. So these are the major gates that anyone is going to interact with. Okay, right. So the logical representation between the output signal and the input signal for a logic gate is represented using a truth table. Okay, so we are going to consider a truth table for all the gates, and at the same time we are going to consider the symbols also. Okay, how they are going to be represented like that. Okay, next. So these are the figures which you can see the symbolic representation of each logic gates. Okay, the first one is the AND gate, and second is the OR gate, and third one is the XOR gate, and this is the buffer, and next is NAND gate. You can see that there is a bubble that is being placed at the output end, and automatically the AND gate is converted into a NAND gate. Likewise, OR is converted into NOR gate, and XOR is converted into XNOR gate, and buffer, that is NOT gate. Okay, right, next. So these are the truth tables for all the gate combinations. Okay, and next topic is buffer. Okay, so what is a buffer? A buffer circuit is a logic circuit for amplifying the current or power. Okay, so what it means, what we discussed for a transistor is also considering for a buffer, and the main activity or the main purpose of a buffer is to amplify the current or power. Okay, right. Next, it increases the driving capability. That means the efficiency or the performance of a logic circuitry can be improved with the help of a buffer circuit or buffer unit. Right, a tri-state buffer is a buffer with output enable control. So how we considered for a transistor, that is a tri-state output configuration, is also considered for a buffer with a tri-state buffer design. And here also we are going to control the operation of a tri-state buffer with a output enable control pin. Okay, so what happens here is when the output enable control is active, that is it is selected, and low, that means the combination is low for active low enable and high for active high enable, automatically the tri-state buffer functions as a normal buffer. That means it is going to be functional as an amplifier. Okay, and the other combination is if the output enable is not active, the output of the buffer remains at high impedance state. That means as we considered for the earlier configuration, that is a tri-state operation. Okay, tri-state buffers are commonly used as drivers for address bus and to select the required device among multiple devices connected to a shared bus. So this is the main advantage. What it means is a tri-state buffers are commonly used as drivers. That means from the available list of devices, so which device is going to be selected, or what device is needed for the concerned operation will be selected with the help of a buffer unit. Okay, so tri-state buffers are available either in unidirectional or bidirectional implementation. Okay, so next is these are the some of the models, that is the unidirectional and bidirectional buffers. The left side figure is unidirectional octal buffer. So here we are having 8 buffers, and these 8 buffers are going to be implemented as in 2 groups, that is 4 and 4. Okay, so for each and every buffer there is a separate output enable control section or output enable line. Likewise, the first half and second half is split up, and this is the IC configuration. And the second picture that is on the right side is for bidirectional tri-state buffer. Okay, right. Next topic is decoder. Okay, so coming to the decoder. So what is decoder? A decoder is a digital IC which is used for to sort out the number of to enhance the number of driving capability at the output section. Likewise, these multiple digital ICs are going to be selected. Okay, so basically a decoder is a logic circuit which generates all the possible combinations of the input signals. Okay, So from the IC number, you can see that the 74138 means it is a 3 to 8 decoder. That means it is having a 3 inputs, and automatically the number of outputs that are available from the 74138 decoder IC is 8. Okay. Next, so decoders are named with their input line numbers and the possible combinations of the input as output. So these are some of the examples: 2 by 4 decoder, 3 by 8 decoder, 4 by 16 decoder. Okay. Next is the 3 to 8 decoder contains 3 input signal lines. Okay, and it is possible to have 8 different configurations with 3 lines. That is from 000 to 111 in the input line. Okay, and accordingly the output is varied from 0 to 7. Okay, with 8 combinations. Right. Next, so this is the block diagram for a decoder. So for input n input lines, we are having m output lines. Okay, and next is, depending on the input signal, the corresponding output line is asserted. For example, you can see in the picture. I will show you the picture first. Okay, so uh, so here you can see in this point for the input state 001. So this is actually represented in a 4 to 1 code. So what is the thing is, the range starts from 000 to 111. Okay, so 000 is the thing which is asserted for the output line 1. So likewise 001 is for output line 2. Okay, and next is, decoders are mainly used for address decoding and chip select signal generation in electronic circuits and are available as ICs. Decoders are mainly used for address decoding and chip select signal generation in electronic circuits and are available as ICs. Okay, so this is the representation, that is IC, 3D decoder IC, and this table is pin specification table. Okay, so let's see the functional table also for the 74138 decoder. Here in this SC diagram, you can see we are having 3 inputs, that is A0, A1, A2, and we're also having 3 different inputs, that is E1 bar, E2 bar, E3. So these are considered to be the enable pins. Okay, so we'll see the importance of enable combinations in the functional table. Okay, so the decoder output is enabled only when the output enable signals E1 bar, E2 bar, and E3 are at logic levels 0, 0, 1. That means the bar that is being placed for any alphabet or for any combinations are considered to be an active low signal. Okay, that means, so what value that you are going to assign for that concerned state will automatically be reversed. Okay, so here we are considering 001. Automatically the value is 111. Then only the decoder operation will be done. Okay, so if the output enabled signals are not at the required logic state, all the output lines are forced to the inactive state. That means, so as the combination that we have given in the earlier thing, that is 001, if it is not available or if it is not selected, automatically all the lines, output lines, are forced to inactive state. That means there is no output response. Okay, next, the output line corresponding to the input state is set low when the output enable signals lines are at the required logic state, that is E1 bar, E2 bar equals to 0 and E3 equals to 1. So this is the valid combination, and automatically the output enable signal lines are at the required logic state. The output line can be directly connected to a chip select pin of a device if the chip select logic of the device is active low. That means the valid combination can be achieved. Okay, right. So this is the functional table. You can see here for the combination, that is 001, for the enable pin configuration is only valid to generate your concerned output combination. So accordingly the inputs selects, that means 0002 111 is the combination, and accordingly for the first input configuration, the first output line will be selected, and automatically you can see here the outputs are also having active low signal cases. Okay, so that is why for the first combination, for the 000, a low output output 0 is having a 0 condition, and remaining are ones. That means all will be reversed, right? So this is going to be a sequential flow. Okay, so 001 for the second, 010 for the third, 011 for four, 100 for five, 101 for 6, 110 for 7, 111 for 8. So these are the combinations. That is for 3 to 8 decoder. Okay. So this is the functional truth table of 3 to 8 decoder. And next is encoder. So what is encoder is exact reverse operation of a decoder. Okay. So the encoder encodes the corresponding input state to a particular output format. The binary encoder encodes the input to a corresponding binary format. Okay. So encoders are named, that means based on the operational combination, that is with inputs and outputs, encoders are defined. Okay. So examples are 4 to 2 decoder, 4 to 2 encoder, 8 to 3 encoder, 16 to 4 encoder likewise. Based on 4 is the input and 2 is the output. So these are the relations. And for a decoder, we are considering that the 8 to 3 encoder contains 8 input signal lines, and it is possible to generate a 3-bit binary output corresponding to the input. That is, inputs are from 0 to 7, whereas the outputs are from 111 to 000. Here we are going to reverse the combination. So let's see the functional table so that you can get an correct idea about decoder and encoder. Okay, so the corresponding output line is asserted in accordance with the input signal. That means, so if the input line 1 is asserted, so automatically what happens is 011 is the selection. Output lines A0, A1 to A2 are asserted as 011. Okay, right. So encoders are mainly used for what purpose? For address decoding and chip select signal generating in electronic circuits, and are available as IC forms. Okay, so you can directly have the encoder IC and you can make use of the encoder IC for your applications directly. So these are the examples of different ICs for encoder operation, that is 8 to 3 encoder IC. Okay, so this is the representation. You can see here 0 to 7 are the inputs, and A0, A1, A2 are the outputs, and these are the conditional pins, that is uh, enable output, enable input, and group select. So you can see here enable input and group select are having bars, that means active low signals they are the. Okay, and next is functional table. You can see the reverse operation, but you can also observe that for highest combination, that is for a 0 combination, you are having the output as all ones. That means this is the reverse operation for a decoder. So for that purpose, you can observe the different combinations. Okay. Yes, welcome back. Today we are going to discuss about multiplexer. So the IC number for multiplexer is IC74LS151. So, okay. So let's see the working condition for a multiplexer. So a multiplexer can be considered as a digital switch which contains multiple input lines and a single line. Okay. So multiplexer is considered to be in case of operational, it will be acting like a digital switch. Okay, so which consists of multiple input lines and a single output line. That means it is going to drive multiple input conditions, and it is going to provide a single output. Okay, and next, so the inputs of mux are said to be multiplexed, otherwise they are considered to be multiplied. Okay, and it is a digital circuit which selects one of the n data inputs and routes it to the ports. That means from the available inputs, or from the available input lines, so what are the required input combinations to perform the valid output operation is going to be selected. Okay, and 74LS151 is the IC that is considered to be a multiplexer operational IC. Okay, and it is a 8 by 1 multiplexer IC. That means it is having 8 input lines and it is going to drive a single output line. This is the representation for your multiplexer IC. Here you can see from D0 to D7 are the inputs, and you are having enable input condition, and you are also having three different select signal cases, and the corresponding outputs are going to be provided on Y and Y bar conditions. Okay, so this is the truth table for functional table for the multiplexer operation. Okay, so only for the don't care condition, that is for the channel select operation, automatically you are not having any valid output for your multiplexer operation. Okay, so and coming to the demultiplexer. So what is a demultiplexer? A demultiplexer performs the reverse operation of a multiplexer. Okay, so got the point. So a multiplexer is having multiple input lines, whereas a demultiplexer is having single input line, like that. Okay, and demultiplexer switches the input signal to the selected output line. So it is going to perform in a reverse manner when compared with the multiplexer. Okay, so the output line to which the input is to be switched is selected by the control lines. So what type of functionality that we are going to realize with the multiplexer? The same functionality is going to be realized with the demultiplexer, but in a reverse manner. Okay, so some of the demultiplexer ICs, that is 1 by 2 demultiplexer IC, NL7SZ18, it is considered to be a typical example for 1 to 2 demultiplexer IC. Okay, and it contains a single input line and two output lines. So by the combination, or with the combination of 1 by 2, automatically that demultiplexer IC is having a single input line, whereas it is going to drive two output lines. Okay, and the output switching is controlled by the output selector control. Okay, so let's see the figure. So this is the representation for your demultiplexer IC. Here you can observe that it is having only a single input, and the corresponding output is going to be appeared based on the select condition. Okay, you can see this is the functional table for the demultiplexer. So for the select cases and with the input combinations for 0001 1011, you are going to have a valid output combinations. Okay, so for both input to a condition and the select case 0, automatically the y naught. So you can directly realize the function here, and the output for y1 is considered to be at high impedance level. Okay, that means no output is going to be presented at the y1 condition. So like that for 0 1 z, and for 1 0 z0, and for 1 1 z1. So these are the combinations for the demultiplexer operations. Okay, next is combinational circuit. What is a combinational circuit? Let's see. So in digital system design, a combinational circuit is a combination of different logic gates. Okay, so these kind of circuits are considered to be useful in implementing different or wide variety of digital logics. Okay, so why? Because they are going to make use of the logic gates. So the output of the combinational circuit is dependent only on the present state of the input at the given point of time. So the combinational circuit response, that is the output from a combinational circuit, is going to be considering or dealing with the present input combination. Okay, so it is not going to deal with any other conditions. Okay, so the combinational circuit do not use any memory. Okay, so that is why it is going to work with the present input combinations. And some of the combinational circuits are some of the ICs which are making use of the ICs which are making use of the combinational logics are the encoders, decoders, multiplexer, demultiplexer, adder circuits, comparators, multiple input gates, etc. Okay, so these are the examples of digital combinational circuits. Okay, a combinational circuit can have n number of inputs and n number of outputs. So this is the combination, and this is the valid circuit realization, and you can see the representation for a block. I mean, for a combination circuit block diagram. So these are the inputs, and these are the outputs. Okay, Next is sequential circuit. What is a sequential circuit? Digital logic circuit whose output at any given point of time depends on both the present and past input is known as sequential circuit. Okay. So for a combination circuit, only present input is considered or taken into condition. For sequential circuits, the present input with a past input combination is considered to be a valid combination. Okay. Next, so hence sequential circuits contain a memory element for holding the previous input states. Okay. So in general, a sequential circuit can be visualized as a combination circuit with memory elements. Okay. So how it is going to deal with the past inputs is automatically your past inputs are going to be stored inside some memory elements or some registers. It will make use of the uh, 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 past input from the register circuit. Okay. And this type of circuit uses previous input, output, clock, and a memory element. Okay. So in addition to the combination circuit operation, a sequential circuit is going to have a memory as one of its combination component. Okay. And this is the representation or a block diagram for the sequential circuits. Here you can see. So here you can see the combination logic circuit is having a feedback from the memory element, and the overall block diagram is going to be a visualization of a sequential circuit. So what happens here is if we provide a memory element with as a feedback section for a combination logic circuit, automatically that particular combination logic circuit is going to transform into a sequential circuit. Okay, next. So flip-flops are considered to be the basic building blocks of sequential circuit. Okay, and sequential circuits are of two types. That is synchronous sequential circuits and asynchronous sequential circuits. So synchronous sequential circuits makes use of the clock signals, whereas asynchronous sequential circuits are non. I mean, they are not going to make use of the clock. So the synchronous sequential circuit operation is synchronized to a clock signal. Synchronous sequential does not require clock. Okay, for an asynchronous sequential circuit, the response depends on the sequence in which the input signal changes. So this is the difference, or this is the change. And let's see the differences between a combination sequential circuit. So we are having some specific differences. That is, the first difference under combination logic circuit is output is a function of the present. It is already discussed. That is, it is considered to be a time independent logic. So whereas coming to a sequential logic circuit, the output is a function of clock, present inputs, and the previous states of the system. Okay. So coming to the combination logic circuit, the second difference is do not have the ability to store data. Why? Because it is not going to make use of any memory sections or memory elements. Whereas for a sequential logic circuits, it needs or it is going to have a memory for storing the uh, present states. Okay, and at later stages it may be used for the reference purpose. Okay, and the third difference is under combination logic circuit, it does not require any feedback. Okay, it simply outputs the input according to the logic design. So coming to the sequential logic circuits, it involves feedback from output to input that is stored in the memory for the next operation. Okay, so as we already seen in the previous slide that a combination logic circuit is provided with memory element as a feedback section. Automatically that particular circuit is going to perform like a sequential logic circuit. Okay, and the fourth is used mainly for arithmetic and boolean operations, that is the combination logic circuits. And coming to the sequential logic circuits used for storing data. Okay, so here we are going to make use of the flip-flops, that is why it is not going to be useful or used for performing the. And the next difference is logic gates are the elementary building blocks, and sequential logic circuits, flip flops are the, and for sequential logic circuits, flip flops are the elementary building blocks. Okay, and combination logic circuits, the next independent of clock and hence does not require triggering to operate. Okay, so they won't make use of, or they are not, they are going to perform are independent of clock signal, and that is why they are not going to require any triggering operation. Okay, and whereas sequential logic circuits, clocked operations are acceptable. And the example for combination logic circuit is adder. That is 1 plus 0 equals 1. That is dependency only on the present input 1 and 0. Okay. So coming to a sequential logic circuit, a counter. That is a counter operation is considered to be a combination of previous output plus 1. That is your current output. Okay. So it depends on the present input as well as previous state. So these are the differences between combination logic circuit and sequential logic circuit. So next is we're going to see the differences between synchronous and asynchronous sequential circuits. Okay. So coming to the synchronous, clock flip-flops act as a memory element in the circuit. All flip-flops are clocked with the same clock signal. Okay. So whereas under asynchronous sequential circuit, unclocked flip-flops are logic gate circuits with feedback loops act as the memory element in the circuit. Okay, so unclocked flip-flops, that means it is not going to make use of any clock signal. So that is why unclocked flip-flops are logic gate circuits. Okay, so the second is the output state of the circuit changes only with the clock breaker. So it is going to make use of the clock as one of its input condition. That is why the output state is the circuit is going to change with the clock breaker input. Okay, and coming to the asynchronous case, the output state change happens instantaneously with change in the input state. Okay, so the last is the speed of operation depends on the maximum supported clock frequency. Okay, completely it is going to deal with the clock signals. That is why the overall speed of operation also depends on the maximum clock frequency. And whereas asynchronous sequential circuits, they are faster than the synchronous sequential circuits. So the next is integrated circuit design, otherwise IC design. Okay, so let's see the thing. So an integrated circuit is a miniaturized form of an electronic circuit containing transistors and other transistors. So what exactly is going to be the combination for an integrated circuit is a combination of your transistors and other supporting passive electronic components. Okay. Next. So in an IC, the circuits required for building the functionality are built on surface of thin silicon wafer. Okay, so hope you got. So we are going to combine all the circuit components or circuit elements for the IC to be functional. Automatically, they are going to build on a silicon wafer section. Okay. Next. The first integrated circuit or IC was designed in the 1950s. Okay, and depending on the number of integrated components, the degree of integration within an integrated circuit is known as. First one is small scale integration. That is, it integrates one or two logic gates per IC. So the example for SSI small scale integration is LS74000. Medium scale integration or MSI. It integrates up to 100 logic gates in an IC. The decade counter 7490 is an example for MSI device. Okay, next is large scale integration, or otherwise LSI. It integrates more than 1000 logic gates in an IC. And the last one is very large scale integration or VLSI. So it integrates millions of logic gates in an IC. Pentium processor is an example of VLSI device. Okay. So these are the different types of integration technologies that are going to be employed for IC design implementations. Okay, and different types of IC designs. So depending on the type of circuits integrated in the IC design is categorized as. First one is digital design. That means purely this category of IC is going to be built with digital IC circuits. Otherwise, the application from the digital design IC concepts is going to implement the digital logic functionalities. Okay, so it deals with the design of integrated circuits handling digital signals. The I/O requirement for such an IC is always digital. So microprocessor or microcontroller, memory, etc. Next one is analog design. Okay, so this analog design deals with the design of integrated circuits handling analog signals and data. So hope you got the difference between digital design and analog design. Okay, so analog design gives more emphasis to the physics
aspects of semiconductor devices such as gain, power dissipation, resistance, etc. Okay, so RFIC design, op-amp design, voltage regulator IC design, etc. are examples for analog IC designs. Okay, and the next one is mixed signal design. Okay, so the combination of digital design plus analog design is considered to be mixed signal design. Okay, and next is what are the various steps involved in HDL? That is hardware description language based design, or otherwise programming based approach. So these are the blocks that are involved, or these are the sections that are involved for a hardware description language based design concept. So the first one is writing up the program, or VHDL language based program description. Next one is functional simulation. So what are the functionalities that are going to be realized from the logic that we have developed? Automatically, we are going to simulate them. After that, we are going to perform the synthesis. So synthesis, at the synthesis phase, we are going to realize the functionality with the corresponding. You can say that the real IC components. Okay, so that is why in the synthesis phase we are going to consider the library functionalities or library inputs with area and timing constraints. And after synthesis operation is completed, automatically it is moved to a placement and routing section. And there we are going to finalize the presence of the logic inside your IC section. And finally, you are going to perform the timing simulation. That is the waveform graph based representation is going to be okay. So these are the steps involved. Next is IO types or IO systems. Next topic is IO types or IO subsystems. Otherwise, input output types are input output subsystems. So the IO subsystem of the embedded system facilitates the interaction of the embedded system with the world. Okay. So what it means is I can say that a microprocessor is going to have an advantage of interacting with the IO sections with the help of IO subsystems. Okay. The interaction happens through the sensors and actuators connected to the input and output ports, respectively, of the embedded system. Okay, so it's already discussed in the unit 1 that the input section of an embedded system is going to have a sensor sections, and the output section of embedded system is going to have the actuator sections. Okay, likewise, they are going to interact with the consent ports, that is, sensors at the input and actuators at the output. Okay, and the sensors may not be directly interfaced to the input ports. So that is why we are going to interface through signal conditioning and translating systems. Okay, that means the response from a sensor output is going to be modified according to the input requirement automatically. Some of the examples that some of the circuits which make use of the sensor output to be converted to the required input for the next circuitry section, that is ADC sections and optocoupler sections. Okay. Next, so these are some of the IO types that we are going to discuss. The first one is LED. Next is 7-segment LED, optocouplers, stepper motors, relays, piezo buzzers, push button switch, keyboard, and last one is programmable peripheral interface. Okay, PPI. First, light emitting diode. So this is the representation. These are the different types of LEDs available. So LED is an important output device for visual indication in any embedded system. What the point? So LEDs are considered to be the output devices for visually representing or providing the status. Okay, in any embedded system, LED can be used as an indicator for the status of various signals or situations. Okay, so ultimately, LED is going to present you with the right information. Automatically, you can identify the status. Okay, of different signal status or some situations. So some of the examples are you can identify the power conditions like device on, battery low, charging of battery. Okay, you can see the representations or you can see the information directly on LED. Okay, next, so LED is considered to be built with a PN junction diode circuitry. It contains anode and cathode. So As usually, how PN junction diode is going to be operational, that is in forward bias condition only. The LED is going to be connected. Okay, so anode to be connected to a positive terminal, cathode to the negative terminal. And what amount of current is needed for the LED to be functional automatically can be controlled with the help of resistor circuits. Okay, so this is the junction based response mechanism, and this is the symbol for your LED. Next is this is the representation of the LED with their concerned part names. Okay, and this is the resistance which is meant to control the current flow inside your LED section. Okay? And the amount of resistance that can be used or that is used is going to base, I mean, is based on the particular formula relation, that is Vs minus VLED by I. So Vs is your source voltage minus the voltage across your LED by. Okay. Next is 7-segment LED display. So the 7-segment LED display is an output device for displaying alphanumeric characteristics. Okay. So a single LED is considered to be used for the status, showing the status. Automatically, a group of LEDs are combined together to form different characters. Okay. So it contains 8 light emitting diode segments arranged in a special form. Out of the 8 LED segments, 7 are used for displaying alphanumeric characters and 1 is used for representing decimal point in decimal number display. Okay, so the LED segments are named A to Z, and the decimal point LED segment is named as DP. Okay, so these are the representations. So this is the 7-segment LED display. You can see 7 segments for representation of alphabet and numerical values, whereas the 8th segment is to represent the decimal point. So these are the programmatic conditions for the 7-segment LED display operations. Okay. Next is the 7-segment LED displays are available in two different configurations. Okay. The first one is common anode and the second one is common cathode. Okay. So in common anode configuration, what it is going to be working with is the anodes of the 8 segments are connected commonly, whereas in the common cathode configuration, the 8 LED segments share a common cathode. Okay. So let's see the pictorial representation. So this is the common anode display. That is, common anode section is considered to be common combination of all the anode terminals, and the common cathode is considered to be the input all the, from all the cathode terminal sections. Okay. Next, 7-segment LED display is a popular choice for low-cost embedded applications like public telephone, call monitoring devices, point of sale terminals, etc. Okay, to represent the characters or to represent the numerical values, so 7-segment LED displays are considered to be the best option with respect to the cost factor. Okay, so these are the combinations. Here you can see numerical representations with different segment combinations. Okay. The next IO type is optocoupler. Okay. So this is the IC form that is available for optocoupler. And optocoupler is a solid state device to isolate two parts of a circuit. Okay. So we are going to split up the or we are going to split up the input section or output section, or otherwise two different application areas inside a single IC is going to be separated with the optocoupler ICs. And optocoupler combines an LED and a photo transistor. So optical or opto in the sense it is going to couple LED with a photo. So this is the representation for the optocoupler. Here you can see this is the diode, that is LED diode, and the response from your LED diode is considered to be an output, and it is considered as one of the input for your transistor. Okay. So that is why the transistor operation is going to depend on the light emission. So it is considered to be a phototransistor. Next, in electronic circuits, an optocoupler is used for suppressing interference in data communication, circuit isolation, high voltage separation, simultaneous separations, and signal intensification purpose, etc. So these are the different applications that are going to be making use of the optocoupler devices. Okay, so optocouplers can be used in either input circuits or in output circuits. So you can make use of the optocouplers at either at input section or at output section. Okay, so this is the representation of this is the combination of an optocoupler at input section and output section. Okay, next is stepper motor. Okay, so a stepper motor is an electromechanical device which generates discrete displacement. Okay. So normally a motor is considered to be a rotational operation. Motor operation is considered to be a rotational. But a stepper motor is considered to be the motion in a stepwise. Okay. The stepper motor is an electromechanical device which generates discrete displacement in response to each other. So okay, it differs from the normal DC motor in its operation. That is why it works with step motions. So the DC motor produces continuous rotation on applying DC voltage, whereas the stepper motor produces discrete rotation in response to the DC voltage applied to it. Okay. So stepper motors are widely used in industrial embedded applications, consumer electronic products, and robotics control systems. Okay. And the paper feed mechanism of a printer or fax machines. It is also almost fax machines are going to work with the stepper motors only. But somehow the operational speed of a stepper motor is a bit low. That is why selection for a stepper motor is not that much suggested. Okay. Next is based on the coil winding arrangements, a two-phase stepper motor is classified into two types, that is unipolar and bipolar. So this is the normal stepper motor representation. And coming to the unipolar stepper motor contains two windings per phase. This unipolar stepper motor contains two windings per phase. The direction of rotation, either clockwise or anti-clockwise, of the stepper motor is controlled by changing the direction of current flow. Okay, so we can operate the unipolar stepper motor in clockwise or anti-clockwise. Okay. The current in one direction flows through one coil, and in the opposite direction flows through the other coil. Okay. So we're going to split up the unipolar stepper motor coil section into two sections. Okay. It is easy to shift the direction of rotation by just switching the terminals of switching the terminals to which the coils are connected. Okay, so let's see the diagrammatic representation. Here you can see the whole coil is split up into two parts, and in this we're going to realize the operation of a unipolar stepper motor. Okay. Next is bipolar. A bipolar stepper motor contains single winding per phase. For reversing the motor rotation, the current flow through the windings is reversed dynamically. It requires complex circuitry for current flow reversal. Okay, and there is one disadvantage of unipolar motors. Torque generated by them is very less. Okay, so why? Because the current is flowing only through the half of the winding, so the winding is split up into two parts. That is why the maximum current cannot be retrieved from the whole coil section. Okay, so hence they are used in low torque applications. So for unipolar motors are considered to be useful in low torque applications. Okay, on the other hand, bipolar stepper motors are a little complex to wire. Why? Because they are considered to be an automatic motors, both clockwise directions and anti-clockwise directions, and the combination of a bipolar stepper motor is going to be considered with a driver IC, that is L293D IC. It is considered to be a H-bridge reversing purpose H-bridge driver IC. But the advantage is that the current will flow through the full coil. Okay, so a bipolar stepper motor operation, in terms of current flow is considered to be flowing through the full coil. The resulting torque generated by the motor is larger as compared to a unipolar motor. Okay, and this is the representation of a bipolar circuit. Okay. Next is the stepping of a stepper motor can be implemented in different ways by changing the sequence of activation of the stator windings. The different stepping modes separated by stepper motors are explained below. The first one is full step. The step mode, in this step mode, both the phases are energized simultaneously. The coils A, B, C, D are energized in the following order. So let's see the table. So here you can see having four coils A, B, C, D, and for the step one motion, automatically uh, at any instance, only two coils are considered to be activated. Remaining two coils are considered to be inactivated. Okay, so step one motion, coil A, coil B are activated. Coil C, coil D are inactivated. Likewise, for step two, coil A and coil D are considered to be inactivated, and coil B, coil C are considered to be likewise coil C, coil D, and next is coil D and coil A. So these are the different step motions. Okay, for a next is it should be noted that out of the two windings, only one winding of phase is energized at a time. Okay. Next. Next step is wave step. In the wave step mode, only one phase is energized at a time, and each coils of the phase is energized alternatively. Okay. The coils A, B, C, D are energized in the following order. So here you can see only corresponding coil is considered to be activated, remaining are considered to be lowered or inactivated. Okay. And the third one is half step. Okay. And the third one is half step. It uses the combination of wave and full step. That is, it is going to implement both the wave step operation and full step operation. So it has the highest torque and stability. The coil energizing sequence for half step is given below. So here you can see we're having 8 steps. Okay, so 4 plus 4. And next is relay. So what is relay? It is an electromechanical device. In embedded applications, the relay unit acts as a dynamic path selectors for signals and power. Okay, so relay circuits are considered to be dynamic path selectors for signals and power. The relay unit contains a relay coil made up of insulated wire on a metal core and a metal armature with one or more acts. Okay, so this is the diagrammatical explanation for our circuit explanation for a relay circuit. And relay works on the electromagnetic principle. When a voltage is applied to the relay coil, current flows through the coil, which in turn generates magnetic field. Okay, so automatically the relay circuits are considered to be working in the electromagnetic principle. Okay, next the magnetic field attracts the armature core and moves the contact point. The movement of the contact point changes the power or signal flow. So this is how the relay operation is considered to be. Okay, so the contact point is going to move from one point to the other point. Okay, so relays are available in different configurations. So let's see the different relay configuration. That is, so this is the overall relay resistance, and this is the internal part of the relay circuit. Next is And the next is the different relay configurations. Single pole, single throw normally open, single pole, single throw normally closed, or single pole double throw. Here, based on the representation, you can get an idea how the switch operation is going to be performed. So the single pole, single throw configuration has only one path for information flow. The path is either open or closed in normal condition. Okay, so this is about the single pole, single throw. Next is for normally open single pole, single throw. Circuit is normally open and it becomes closed when the relay is energized. And for the last single pole, normally closed single pole, single throw configuration, the circuit is normally closed and becomes open when the relay is energized. And the last is for single pole double throw relay. There are two points for information flow, and they are selected by energizing and energizing the relay. So based on the design a combination for a relay configuration, single pole double throw is preferred. Okay. Next, so we're having a type of relay circuits for embedded systems. There are read relays, So these are the special relays for embedded applications which require switching voltages. Okay, it works with DC voltage. Next is piezo buzzer. So what is piezo buzzer? It is a piezoelectric device for generating audio indications in embedded applications. Okay, and a piezoelectric buzzer contains a piezoelectric diaphragm which produces audible sound in audio in response to the voltage applied to it. Okay, so a piezoelectric buzzer contains a piezoelectric diaphragm. Okay, that means the implementation of a piezo buzzer can be. The piezo buzzer is a piezoelectric device for generating audio indications in embedded applications, and a piezo buzzer contains a piezoelectric diaphragm. That means what is piezo effect? By applying some force, automatically that material is going to produce some electricity. So that is a mechanism. So a piezoelectric buzzer contains a piezoelectric diaphragm which produces audible sound in response to the voltage. Next, there are two types of piezoelectric buzzers. The first one is self-driving, the second one is external driving. So the self-driving circuit contains all the necessary components to generate sound at a predefined tone. That means self-driving piezo buzzer components are considered to be the components which are intended to produce a single predefined tone. Okay. So whereas external driving piezo buzzer supports the generation of different tones, a tone can be varied by applying a variable pulse train to the piezoelectric buzzer. Okay, and these are the different models. So this is the diagram. This is the speaker section. Okay. Next is push button switch. So it is an input device. Push button switch comes in two configurations, namely push to make and push to break. So in the push to make configuration, automatically the switch is normally in the open state and it makes a circuit contact when it is pushed or pressed. Okay. In push to break, the switch is normally in the closed state and it breaks the circuit contact when it is pushed or pressed. So these are the two different configurations. In embedded applications, push buttons is generally used as a reset and start switches. Okay. So hope you got an idea what is the exact purpose of a push button switch. And these are the combinational circuits. Next is keyboard. So keyboard is an input device for user interfaces. If the number of keys required is very limited, push button switches can be used. Okay, and they can be directly interfaced to the port pins for reading. So instead of making use of a keyboard, we can make use of a push button when the number of keys that are required for the operation are less. Okay. Next, so the default keyboard layout is matrix keyboard layout. So it is considered to be an optimum solution for handling large key requirements. Okay, and example is for interfacing 16 keys in the direct interfacing technique, 16 port pins are required. So whereas matrix keyboard only requires 8 lines, that is 16 keys are arranged in a column of 4 bars. For example, for interfacing 16 keys, the direct interfacing technique, 16 port pins are required. Whereas the matrix keyboard, only 8 lines are required. Okay, so I hope you got the difference, or I hope you identify the difference. 16 keys are arranged in a column, that is 4 by 4 matrix form. Okay, so this is the matrix keyboard layout. Here you can see we're having a total of 16 combinations. But overall, the driving of the 16 combinations with 4 by 4 matrix. Next is PPI, or Programmable Peripheral Interface. These devices are used for extending the I/O capabilities of processors. So PPI provides the extended support for I/O and data ports for processors. Okay, so this is considered to be an additional IC or external IC to be used to interface with your processor with your I/O sections. Okay. An example is 8255 PPI, that is Programmable Peripheral Interface Component IC. Okay. The next one is serial communication devices. Okay.
So next is serial communication devices. Okay. So serial communication is considered to be a common method of transmitting data between a computer and a peripheral device. Okay. such as a programmable instrument or even another. So, serial communication transmits data of one bit at a time sequentially over a single communication line to a receiver. That means the path between a transmitter and a receiver to transmit a serial data will be in a single line. Okay, that is the path is single. Okay, and serial communication method is considered to be most popular communication protocol, which is being used in many devices for instrumentation. Okay, and it is a popular technique because serial communication devices will not require any extra hardware to be accessed or otherwise to be used. Okay, and these are some of the different serial communication protocols which are considered to be useful. So RS-232, RS-423, RS-485 are considered to be the serial asynchronous communication mediums. RS stands for recommended standard, and USB is going to implement both parallel and serial communication. Firewire is the technology from Apple company, that is IEEE 1394 port, and Ethernet is a LAN, that is RJ45 pin, and MIDI is the media interfacing bus port, and PCI is a programmable component interface express bus. That is, it is going to implement the serial communication, and serial peripheral interface and serial communication interface ports are also considered to be the serial communication devices ports. And I2C inter-integrated circuit, and last one is infrared. Okay, and next is parallel device ports. So parallel ports are the perfect choice for connection to other peripheral devices. Okay, why? Because we can achieve more data rates with more data speeds. Okay, and the communication to peripheral access using a parallel port is considered to be limited. Why? Because there is no such standard specification for the interface. Okay, so the IEEE 1284 in the year 1994 is considered to be a parallel port standard, which is based on the Centronics company, that is SPP port standard specification, and it includes enhanced parallel port and extended capabilities port. Okay, so these are some of the parallel device ports. IBM system is going to make use of a parallel port, which is known as a 360 direct control feature in the year 1964, and ISA, ATA, SCSI, PCI, and front side bus. These are some of the parallel ports which are available inside your laptop or desktop systems. And IEEE 1284, that is Centronics printer port, is considered to be ubiquitous, once ubiquitous. And the last one is IEEE 48, that is meant for laboratory instrumentation bus purpose. Okay. So the next is wireless devices. So the name wireless means the connectivity is going to be accessed through wireless means. Okay, so no wires are going to be in presence. Okay, so wireless communication is the transfer of information or power between two or more points that are not connected by an electrical conductor. Okay, so here the electrical conductor is considered to be a copper wire, which is going to be a medium between a transmitter and a receiver. Okay, so here we're going to transmit, or we're going to transfer information or power. Okay, next. So the common wireless technologies is the radio wave technology. Okay, so I mean the most common wireless technology is wireless. I mean radio technology, radio frequency based technology. So with radio waves, the distances, that means that the communication phenomena, the communication mechanism going to be implemented can be very short. That is a few meter range for television communication, television to remote communication, or it can be extended thousands or even millions of kilometers for deep space radio communications. Okay, so this is how wireless technology or wireless communication implements. And next, it encompasses various types of fixed mobile and portable applications, which includes two-way radio, cellular telephones, PDAs, and wireless networking. So, okay, so automatically wireless implementation is going to override the wired implementations. Okay, right. So next. Some of the applications which makes use of the wireless implementations are GPS units, garage door openers, wireless computer mice, keyboards and headsets, headphones, radio receivers, satellite television broadcast, and cordless telephones. Okay, so all these what I can say is all these equipment will make use of the wireless means of communication procedures. Okay, right. So the primary usage of wireless is of avoiding wires or cables. That means why we are opting for a wireless implementation is to avoid wires. Okay, the layout of the wires is going to be avoided completely. And some of the types of wireless implementations are the LTE network, that is a cellular network. LTE stands for long-term evolution, and LTE advanced is a technology which is held with the 4G wireless cellular technology, that is VoLTE technology, that is voice over long-term evolution, and Wi-Fi and Bluetooth. Okay, so these are some of the types of wireless communication implementations. Okay, and next is timer and counting devices. Okay, so what is a timer and what is a counter? So let's see the things. A timer is a device which counts the input at regular intervals. That means we are going to take the interval, represent the interval as dot t. Okay, using clock pulses at its input. That means a timer is going to have an input of clock pulses. So automatically it is going to count the clock pulses. Right, next. So the counts increment on each pulse and stores it in a register called count registers. Okay, so hope you got an idea. So a timer is going to count the clock pulses, and accordingly the counter is going to store the timer operational values. Okay, or output values. Okay. Next, so the output bits in a count register are at the output pins are for the present counts. That means what is the data that is held with a count register are at the output pins of a counter is considered to be a value which is related to the present count operation. Okay, and the counts multiplied by the interval. That means in order to find out the interval between any two time instances, automatically the relation is the present counts minus initial counts into the interval, that is dot t. Okay, so this relation will give you the interval between any two instances. Okay, so a device which counts the input due to events at irregular or regular intervals. That means I can say that a timer operation is considered to be a operation which is a scheduled or a normal operation. Okay, that means the count gives the number of input events or pulses since it was last read. Okay, so it also has a register which enables the read of present counts. Okay, so it also equips or equipped with a register which is needful to identify the present count values. Okay, so it also functions as a counter when counting regular interval clock pulses. Okay, so the timer operation can be realized as a counter operation when counting the regular interval clock pulses. So it has an input pin for resetting it for all count bits equals to zeros. Okay, so automatically a counter or a reset I mean the register value to be resetted is going to be done from the input pin where the input pin condition is set for all zeros. Okay, right. So it has also an output pin for output when all count bits equals to 0 after reaching the maximum value. That means for output condition, if the maximum value is reached, automatically the reset operation must be done. Okay, or otherwise a timeout condition or overflow condition occurs automatically. For that particular combinations or conditions also, the reset operation must be done for a counter. Okay, and next is when a timer or counter becomes, so these are the address ranges or the maximum range of addresses that are assigned to a register, that is 0 by 00 or 0 by 4 zeros, that is a 4-bit address value. The maximum is 0 by ff or 0 by fff. Okay, maximum value. So it can generate an interrupt. That means if a minimum address range or maximum address range is reached, automatically the status or the particular condition is going to be identified as an interrupt, or an output or timeout is going to be occurred, or it automatically sets a status bit as TOV, that is timer overflow condition. Okay, so all these status or all these output conditions are considered to be counter related reset operation purpose. Okay, and next is, so this is the representation for a timer cum counting device block diagram, and it is having different blocks. The first one is the it is internal clock pulses generation block, and it is fed to a pre-scaler unit where the number of the clock pulses are going to be pre I mean scaling the that means what amount of clock intervals are needed automatically will be scaled, and after that it is going to be fed to your timer unit, and the timer is having different functionalities, timer start, timer stop, and timer enable, and automatically the timer is going to count the up count values, whereas it is also going to count the down count operations. Okay, so if the down count is happening, automatically it is considered to be a false condition. Okay, the timer is only considered to count the up count operations. Okay, and you are having a timeout condition also, that is identified as an interrupt, and the maximum count is considered as a variable which is between 0 and 2 power n minus 1. Okay, so we are also having a load enable condition, that is initial count is equals to set for 2 power n minus 1. So based on the count range, automatically the count operation will be continued, and it is also having some different flags for storing the status conditions and control variable inputs. Okay, and next is a free running counter, or otherwise it is known as a blind running counter. So what is the difference between a normal counter and a blind running counter is, a counting device may be free running or a blind counting device giving overflow interrupts at fixed intervals. That means this particular counter register is not considered to be operating with a predefined conditional values. Okay, so automatically it is going to generate a overflow interrupt outputs. Okay, so a pre-scaler for the clock input pulses to fix the interval. That means for a free running counter, there is no conditional case for operational purpose. Automatically, the pre-scaler unit will do the necessary action. That means it is going to fix the intervals for the free running counter operations. Okay, so it is useful. That means the free running counter is going to be useful for action or initiating chain of actions. That means if we want to implement a continuous counting operations, we can go with the free running counter, or otherwise if we want to interrupt the processor in its operational functionalities at preset instances, that means at predefined intervals, if we want to interrupt the processor activities, automatically we can interrupt. And the third one is noting the instances of occurrence of the events can be identified by the free running counter. And fourth one is processor interrupts for requesting the processor to use the capturing of counts at the input instance. That means if the processor is busy with other functionalities or other activities, automatically the processor is going to be identified to initiate the counting operation for the input input instance. And the last one is, it is going to be useful for comparing of counts on the events for future actions. Okay, so these are the uses of a free running counter. Okay, and this is the block diagram for the free running counter. Here you can see uh, uh, the pre-scaler unit is considered to be the most important unit for a free running counter device. Okay, and the remaining rest of the things are normal with a normal counter operation. Okay, and the next is, the timers are very essential for generating precise time difference in any system. Okay, so for any CPU, it needs to maintain or it needs to perform its actions according to the time intervals. Okay, so timers can be implemented in either software or hardware. That means we can perform the timer operation through software mechanism or hardware mechanism. That is an optional thing. Okay, right. So hardware timers are more dedicated units. Why? Because the hardware functionality, the hardware feature is going to be programmed in such a manner that that the ICs are considered to be a dedicated ICs. Okay, and the response from the hardware timers are ultimately high precise. Okay, And the 8051 microcontroller is having a hardware timer functionality or feature that can be configured. It is having a 16-bit hardware timer functionality that can be configured to operate in either timer mode or external event counting mode. Okay, so you can perform either timer operations or counter operations according to the need. Okay, so the next is a timer counter. I mean, we are going to see the frame format for different registers that are going to be useful for timer or counter operations. The first one is the T mode register, or otherwise timer mode control register. So it is known as a special function register of 89H. This is the address range. So this is the frame format. It is divided into two parts, that is timer 0 configuration and timer 1 configuration. Overall, we are having 8 blocks or 8 frames. So the frames are same for timer 0 and timer 1 configuration. The first one is gate frame and counter a timer operation. Memory is M1 and M0. Likewise for timer 0 selection. And next register is TCON register, that is timer control register. It is known as SFR88H, and it is having different flag registers. So timer flag, timer register, timer flag, timer register, interrupt enable, interrupt timer register. Okay, so these are the different frames. So the next one is watchdog timer. So what is watchdog timer? So in any, a normal system, normal laptop or normal computer is having a feature of overcoming the situation of any unknown condition that is being raised with some application situations. Okay, or otherwise with some application there may be a chance of hanging status or some hang up status within your CPU. Automatically it can be avoided by applying key combination from your uh, uh, keyboard. Okay, so that is if we operate the control alt delete operation, automatically we can get the task manager window. From there we can terminate the particular application which is behaving in an abnormal way. So this is the feature that is available with the normal systems. But what about embedded systems? So the embedded systems is going to make use of the watchdog timer to come out of the situation where where the embedded system is not going to make use of the much more hardware specifications. Okay, so right. So a watchdog timer, or simply a watchdog, is a hardware timer for monitoring the firmware execution. Okay, so what is the purpose of a watchdog timer? Is it is going to monitor all the firmware execution cycles. Okay, so depending on the internal implementation, a watchdog timer is going to perform an increment operation or a decrement. So depending on the internal implementation, the watchdog timer increments or decrements. So it is a normal timer operation. So according to the each clock pulse that is being generated, and at what time the reset operation is needed, that is at the processor end, it is based on the number of count operations that are performed. That means if the count value reaches the 0 for a down counting operation, automatically there needs to be a reset operation to be performed, or otherwise for a highest count value that is obtained for a upcounting watchdog, then it must reset its operation. So okay, so if watchdog counter is in the enable state, that means if it is work in active state, automatically the firmware can write a 0 value. That means the firmware condition, the firmware execution cycle can write a 0 value for upcount to it before starting the execution of a piece of code. That means the firmware execution is going to be monitored by watchdog timer, and accordingly it is going to write a 0 value. That means it is considered to be a count operation. That means from 0 the count value will be incremented, and automatically a watchdog will start its counting operation. Okay, right. So if the firmware execution does not complete due to some malfunctioning, automatically within the time frame that is required by the watchdog timer to reach the maximum count, the counter will generate a reset pulse. So this is done automatically, and with this your processor is going to reset its operation. Okay, and next is so this is the block diagram for your watchdog timer unit, and here you can see the watchdog timer is connected to your microprocessor or microcontroller with two different connections. That is, one is the reset pin from watchdog timer to reset to your processor response, and from processor to your watchdog timer is connected with the watchdog reset pin or operation. And there is a common system clock for both the microprocessor and the watchdog timer. So why? Because a synchronous activity must be held between microprocessor and a watchdog operation. Okay, and in this watchdog timer, you can see a free running counter is going to be used. That means n number of counting pulses must be needed for a watchdog timer unit. So that is why a free running counter operation is used here. Okay, and next, so if the firmware execution completes before the expiration of the watchdog timer, automatically a reset operation can be performed by counting with the count operation by writing a 0 to the watchdog timer register. Okay. So, if the firmware execution completes before the expiration, that means within the specified time interval, if the work is done automatically, it is considered to be a good thing. But for the watchdog timer, there is an exceptional case. That means the time specified for the timer unit to complete its execution cycle, automatically the watchdog timer is going to complete before the expiration. Then automatically you can reset the count operation by writing a 0 to the watchdog timer register. That means it is a exceptional thing that we can reset the, or we can reset the watchdog timer operation by writing a 0 into the register. That is a watchdog timer register. So this is at the I mean, this operation is going to be performed by the programmer. Okay, right. Next, so most of the processors implement Watchdog as built-in component. That means this is going to be available in the form of a IC, and it is going to provide you the status register to control the Watchdog timer operation. That means enabling and disabling the Watchdog functionality. And Watchdog timer register is meant for writing the count value operations. Okay, and if the processor or controller does not contain a built-in Watchdog timer, that means if the watchdog timer is not available as a internal IC, automatically it can be accessed external. External interfacing is also available. Okay, the same can be implemented. So if the processor or controller does not contain a built-in watchdog timer, the same can be implemented using an external watchdog timer. So if the watchdog timer is not available in built, automatically, so if the processor or controller does not contain a built-in watchdog timer, the same can be implemented using an external watchdog timer IC circuit. Okay, so this is the advantage that is going to be available with watchdog timer IC. So it can be interfaced externally to the CPU section. Okay, and external watchdog timer uses hardware logic for enabling and disabling. That means they are interfaced externally and they are going to have their own control mechanism. So likewise, they are having their hardware logic for enabling and disabling functionality and resetting the watchdog count, etc. Instead of firmware based writing. That means the firmware exceptional thing is going to be performed internal to the activity, and here for external interface it is not available. And the microprocessor supervisor IC, that is DS1232, is considered to be an external interface watchdog timer IC. Okay, and in modern systems, that means what happens with the watchdog timer operation or watchdog timer response is every time the processor is going to be resetted. So this makes the overall execution time to be increased. So what happens is the watchdog timer need not to be interrupt the processor every time for its functionality. Automatically, the watch so that the functionality of a watchdog timer can be identified as an interrupt, and the CPU will not be resetted every time with the watchdog timer response. So this is the updated thing that is held with the watchdog timer operations. Okay.
So the interrupt handler for this handles the situations in an appropriate fashion. So what happens with the watchdog response, watchdog timer response is it is going to be identified as an interrupt, and automatically the interrupt handler mechanism will take over the interrupt conditions, and it will do the necessary actions. Okay. So the next is real-time clock, in short RTC unit. Okay. So the real-time clock is a system component responsible for keeping track of time. Okay. So it holds the information like current time in hours, minutes, and seconds, and also in 12-hour format or 24-hour format with date, month, year, day of the week, etc. And all this information is going to be supplied as a timing reference to the system unit, or otherwise to your CPU section. Okay. So RTC is intended to function even in the absence of power. Okay. So the CPU needs to keep a note of the activities or the functionalities that are going inside. So it needs to create, or it will create a log report. So accordingly, it will note down the time intervals or timing conditions. So RTC must be functional even in the absence of power. Okay. So RTCs are available in the form of integrated circuits from different semiconductor manufacturers like Maxim or Dulles, ST Microelectronics, etc. Okay, so the RTC chip contains a microchip for holding the time and data related information, and a backup battery cell for functioning in the absence of power. Okay, so it is going to have a IC section to perform the, I mean, the microchip section to perform the time and date related operations, and a backup battery cell for functioning in the absence of power. So overall, these are all combined together and are built on a single IC package. Okay. So this is the representation of RTC unit. So here you can see this is the microchip which is going to store the or perform the time and date related operations, and this is the oscillator circuit or oscillator unit, and this is the battery for backup. Okay. And the next is the RTC chip is interfaced to the processor or controller of the embedded system, and for operating system based embedded devices, a timing reference is essential for synchronizing the operations of the OS kernel. So what it means is the OS is having the kernel unit or kernel functionality. So every application is going to be operated in the presence of the kernel control. Okay. So that is why a kernel is going to take a note of all the applications, and it will maintain a log report accordingly. So for synchronizing the application operations or the operations with the OS kernel, the timing reference is mandatory. Okay. And that timing reference is going to be retrieved or is going to be taken from the RTC chip. And next, the RTC can interrupt the OS kernel by asserting the interrupt line of the processor or controller to which the RTC interrupt line is connected. What it means is the response of a RTC can be known as an interrupt. It is to the OS kernel section by asserting the interrupt line. That means, so the whenever the RTC functionality needs to be resetted or otherwise something to be done with the RTC section, automatically the response is going to be given directly by interrupt to the OS kernel section using the interrupt line. Okay, so the response given from the RTC section to a OS kernel section will be identified in the terms of IRQ, that is interrupt request number generated by an interrupt controller. So one IRQ can be assigned to the RTC interrupt, and the kernel can perform the necessary operations. Like that means the RTC section needs to be perform a maintenance from the kernel section, and automatically based on the interrupt that is being generated from the RTC section, the kernel will perform the necessary operations like system date time updating, managing software timers, etc. So when our RTC time tick interrupt occurs. Okay. And RTC can be configured to interrupt the processor at predefined intervals or to interrupt the processor when RTC register reaches a specified value. That is a maximum value or maximum range that RTC register reaches automatically. It can interrupt the processor operation, or otherwise the RTC can be configured to interrupt the processor at predefined intervals. So I can say that the alarm operation that is available inside your mobile or somewhere, digital alarm operation is directly related to the RTC operations. Okay, right.
So thank you very much. Hope you got a very good idea about the hardware components. What are going to be used for embedded design, embedded product designs. Okay. So with this, we covered all the hardware requirements that are needed for the embedded products in a better manner. Okay. Thank you very much.